Alright, in this video we're going to be talking about a very important concept that is used all throughout electronics, that is the operational amplifier, or simply op-amp. So essentially there's this device that is sort of like a black box. It has a bunch of stuff inside that we don't actually care much about because we essentially just use this thing as a whole when we're creating electronic circuits. But in general, there are a few properties that are important to be aware of. So the basic thing an amplifier does is it amplifies the signal. So you give it some input voltage or input current, and then it would output some voltage. It could be higher or lower depending on how you set it up. So there are essentially four main inputs. There are two on the terminals here, so positive and negative from the input voltage signal. And then over here you have the power supply voltage. So these devices are usually for electronic circuits, so they operate in the range between 5 and 15 volts of power. What that means is that you're always going to be limited because we know that there's no way you could put out more voltage than you put in. So obviously these devices are limited to operating within this range. So the output voltage can never be higher than the supply voltage. That's one of the main things that we need to know about amplifiers. The next thing is that the gain is determined by resistors that are placed around. So this is a very basic kind of design. So in order to actually use an amplifier, we need to place loads around it. We need to connect it to ground in certain places and all those different things. So this is essentially just basically showing you the main diagram that is used in schematics. So there are a few ideal characteristics of op-amps, and in fact there are three very important characteristics that we need to know about. So ideal means that we're assuming everything is perfect, everything is the way we want it to be, but this is still quite useful because it is the starting point for any design or analysis that we use with op-amps. Now the first one is the input impedance is almost infinite, so the inputs should draw no current. This is very important because what it is saying is that the current that is coming in from the terminals positive and negative should be zero at all times, assuming that the op-amp is operating under ideal characteristics or in an ideal situation. Now, one other thing that I should mention is that this is usually called the non-inverting terminal, and this is the inverting terminal. That's just jargon that is used with op-amps, but at least you know that it basically refers to the polarity of these two inputs. The second op-amp rule says that the difference in the input voltage should be zero, so that means that the voltage coming in at this terminal and this terminal should be the same. So V in positive should be equal to V in at the negative terminal. And then the third characteristic that we need to be aware of is that if we ever have a situation in which we calculate the output voltage to be greater than the supply voltage, then that means that the op-amp is operating under a saturated condition, or it is becoming saturated, and thus that means that we need to recalculate everything that we just did, so all the currents and voltages, by essentially assuming that the output voltage is exactly equal to the supply voltage. So basically, if we ever get a situation in which we calculate the output voltage and it comes out as greater than the supply voltage, then we know that we have done something wrong, and then we have to recalculate everything by simply assuming that these two are equal to each other. And we're going to look more into saturation and what that means in terms of op-amps in later videos. For now, what we're going to do is we're going to look at a very simple example. So we have an op-amp over here. As you can see, we have the positive terminal connected to ground, and then we have two resistors R1 and R2. We have an input voltage signal coming in from this side, and then we want to determine the voltage out in terms of that. So we want to find out the gain, by how much is the voltage changing with respect to the input. Now, in order to analyze any op-amp circuit, we need to use it. We basically perform the analysis using this ideal op-amp characteristics. So the first one I'd like to look at is, okay, so what is going to be the voltage or the potential at the inputs? In this case, we notice that the potential from the positive terminal is going to be zero, and assuming ideal op-amp operation, then the voltage over here should be equal to zero. So the first thing we notice is that V plus should be equal to V minus, which is equal to 0 volts. That's the first realization we need to make. Now if we take in the current that is coming in from this side, we're going to call that I1. Then we know that I1 is going to be equal to the drop in potential, which is in this case Vin minus 0, Vin minus 0 divided by R1, which is simply Vin divided by resistor 1. Okay, now the next thing we're going to do is we know that the inputs should draw no current, which means that at this node over here, we have current I1 coming in. Then we have current I2 coming out, which goes into the second resistor. And since the terminals should draw no current, we know that whatever current is coming in from this end is going to be 0. So by KCL, we know that I1 should be equal to I2 because of conservation of electric charge. All the current coming in here should go in this direction. So the next thing we know is that I2 should be equal to I1, which is equal to Vin divided by R1. And now to find out V0, or essentially the current through R2, well, we know that that's basically that. Now we have V0 minus the voltage at this terminal here, but essentially it would actually be in the opposite direction because we know the current is coming from this terminal to that terminal. So in this case, we would actually write down, so I2 is going to be equal to 0 minus V0, so it is going in this direction, divided by R2, which is essentially just this resistor. And then we know that this should be equal to Vin divided by R1. Okay, so according to our op-amp rules, this is essentially what we have derived. So using this equation, we can now express V0 in terms of Vin. So V0 is going to be equal to minus R2 divided by R1 times Vin. And thus we notice two things here. The gain A is going to be equal to minus R2 divided by R1. So it is just going to be the ratio of R2 and R1. So normally the resistor that we place across the op-amp, we call it the load. And in this case, what the negative sign is telling us is that we're essentially inverting the input signal. So suppose that we have a sinusoidal input voltage that looks something like this. Then essentially what this is doing is the output voltage, so let's say this is Vin. Then the output voltage, which I'm going to draw in red, is going to look something like this. So every single peak is essentially getting inverted. The phase is the same. The phase does not change. Only the amplitude of the input voltage waveform changes. But I'm assuming that in this case R2 is less than R1. So the output voltage V0 is actually going to be less. The amplitude of it is going to be less than Vin. But if R2 is greater than R1, then we're going to have a waveform that is still going to be inverted, but it is going to be larger in amplitude than Vin. So that's the basic principle of an inverting operational amplifier. So this configuration is called the inverting op-amp. Alright, so that's basically the main building block of op-amps that we're going to be looking at, and it's a very important result. And hopefully this gives you a good idea of how we can start by using these very basic ideal op-amp characteristics to analyze circuits involving operational amplifiers. And then in the next videos we're going to be looking at some other examples that involve op-amps and how they can be used for different applications in electronics.